Hello, fellow bags of water. This is Roger Jones, and I'm coming to you from steamy downtown Pensacola, Florida. Today, I want to talk about a very special set of chemical bonds that enable the actions of living things, that enable life to do something beyond existing. These bonds are called hydrophilic and hydrophobic bonds. In an earlier post, we pointed out that the stability of life, that its ability to last a while, is a result of the strength of covalent bonds. These are the kinds of bonds that attach hydrogen to oxygen in water, for instance. Molecules held together by covalent bonds are very stable at temperatures most biology lives at. But we noted that life must do more than exist. If all life does is exist, it's a rock. Life must also do something, and even do it repeatedly. This something is called metabolism in the biological world. And we must have some weaker bonds that break more easily to support the faster behavior of metabolism. Fortunately, there are other types of bonds that do have energies similar to the energies of thermal water molecules. These bonds are typically of an electrical nature as opposed to quantum nature that covalent bonds are. Because the energy of these bonds is closer to thermal energy of water molecules, collisions break them apart quite regularly. In fact, when observing these bonds, like in a simulation, it's quite difficult to tell that bonding has occurred at all. Yet the effect of these bonds is biologically significant. So let's take a closer look at this type of bonding. What happens when a material dissolves in water? Let's take the example of salt, table salt, which is composed of one atom of sodium and one atom of chlorine. When sodium chloride is placed in water, the molecule dissociates into a positive sodium ion, which is light blue in this little simulation, and a negative chlorine ion, which is I haven't shown. Quantum effects cause the chlorine nucleus to grab an electron from the sodium nucleus, and that's how that happened. The simulation illustrates what happens around the sodium ion. The negative oxygen ions in water are attracted to the positive sodium. The negative oxygen atoms are the blue atoms in the water molecule. The positive hydrogen atoms are repelled by the positive sodium. And something similar happens around the chlorine. The positive hydrogen atoms are attracted to the negative chlorine, and the negative oxygen atoms are repelled by the negative chlorine. This is all very similar to how a particular water molecule interacts with the rest of water molecules. The positive and negative poles of the particular water molecule behave similarly to the explicitly charged sodium and chlorine. In general, charged or polar molecules behave similarly to water molecules. This allows them to dissolve in water. It allows them to mix with water at the molecular level. Well, everyone is aware that oil and water do not mix. It has even made it into the lexicon as a metaphor for incompatibility in general. No matter how much you stir oil and water together, the oil separates from the water and floats to the top. This is called the hydrophobic effect. Hydro meaning water, phobic meaning fear, so the oil is afraid of the water. The hydrophobic effect is poorly understood. We'll present in this adventure a primitive picture of the effect, and we'll go a little bit deeper in a later post. The effect is a consequence of the fact that molecules that make up oil, or lipids as they're called in biology, are uncharged. And there's very little localized charge anywhere on the molecule. So unlike the water molecule, which has kind of a separation of charge with more negative charge towards the oxygen atom and more positive charge to the hydrogen atoms, lipid molecules, oil molecules, don't have this separation of charge. So it's electrically neutral all around the molecule. So water molecules, which are charged, cannot interact very well with these lipid molecules that are uncharged. So the interaction of oil with water is a consequence of oil molecules disrupting the preferred interactions of water molecules. That is, water molecules trying to neutralize their charges. Lipid molecules repel water molecules because water molecules are able to attract each other better when they are not in the presence of a lipid molecule. And so I'll go into this a little bit deeper in the next post. The display illustrates a simple lipid molecule surrounded by 4 water molecules. The water molecules are in a very fragile state connected to each other by these electrostatic bonds we call hydrogen bonds. The water molecules encircle the lipid. They do not interact with the lipid electrostatically because lipid molecules are not charged, nor do they have localized charge distributions. This causes the water molecules to lie flat on the lipid molecule with both positive and negative domains of the water molecule right up against the lipid. If you click the start button, you can see the water molecules find this fragile equilibrium. If the toggle is on, the equilibrium is one in which water molecules engage the lipid molecule. Because this equilibrium is unstable, we use some numerical tricks to direct the system to the state. If the toggle is turned off, the numerical tricks are turned off and the system reverts to its natural state. In that case, you see the water molecules slide off the lipid and move away from the oil. The bottom line is that water molecules near the lipid interact with other water molecules near the lipid to cause the molecules to slide away from the lipid. This is called the hydrophobic effect. Hydrophilic and hydrophobic effects become biologically interesting when a molecule has both water and lipid characteristics. For instance, there's a class of molecules called proteins that are composed of long chains of smaller molecules called amino acids. Some amino acids are hydrophobic, while others are hydrophilic. When proteins are placed in water, the hydrophobic amino acids try to avoid the water, while the hydrophilic amino acids are attracted to the water. This causes the protein to fold into a globular 3D shape, which is characteristic of that particular protein. This shape has the lipid amino acids in the middle of the globule to avoid the water, and the hydrophilic amino acids on the surface of the globule that is attracted to the water. Well, happy bags of water. That's it for today. This is Roger Jones signing off from steamy downtown Pensacola. If you'd like to meet up again, please subscribe at the end of this video or somewhere below. And I'm looking forward to seeing you then. Bye bye.